Welcome to the Padhai Kar Lo JEE preparation channel. You can practice more problems on this exact topic on our Padhai Kar Lo Android app, link in the description below, or on our website padhaikarlo.com. Today's chapter is Electrochemistry, a chapter that connects redox chemistry directly to real, quantitative electrical measurements, and is one of the most numerically rich, formula-heavy chapters in the entire JEE chemistry syllabus. In this video we'll cover galvanic cells and cell notation, standard electrode potentials, the Nernst equation, conductance and molar conductivity, Faraday's laws of electrolysis, and batteries and corrosion. Let's begin. A galvanic or voltaic cell converts spontaneous chemical redox energy directly into usable electrical energy by physically separating the oxidation and reduction half reactions into two distinct half cells, connected externally through a wire, allowing electron flow, and internally through a salt bridge which maintains overall electrical neutrality by allowing ion migration between the two half cells. Oxidation, genuine electron loss, always occurs at the anode, which is specifically the negative terminal in a galvanic cell, while reduction, genuine electron gain, always occurs at the cathode, the positive terminal. And remembering this pairing correctly, an oxidation anode versus a reduction cathode, and specifically that this exact terminal polarity reverses in an electrolytic cell, is a classic, frequently tested point of confusion. Standard cell notation represents the complete cell compactly, anode components written on the left, cathode components on the right. A single vertical line representing a phase boundary between electrode and solution, and a double vertical line specifically representing the salt bridge. For the classic Daniell cell, this is written zinc, solid, zinc 2 plus aqueous, double line, copper 2 plus aqueous, copper, solid. Cell potential E cell equals cathode reduction potential minus anode reduction potential, and a genuinely positive E cell value confirms the reaction is spontaneous, exactly as written directly connecting back to the thermodynamic relationship. Delta G equals minus NF E cell, meaning a positive cell potential necessarily corresponds to a negative, spontaneous Gibbs free energy change. Standard electrode potential is measured relative to the standard hydrogen electrode, arbitrarily assigned a value of exactly 0 volts, under standard conditions, 1 molar concentration, 1 atmosphere pressure, 25 degrees Celsius, and every other electrode's potential is measured specifically as a reduction potential relative to this fixed reference point. The electrochemical series arranges elements in order of their standard reduction potentials, and this ordering directly immediately tells you relative oxidizing and reducing strength. An element with a highly positive reduction potential, like fluorine, is a genuinely strong oxidizing agent readily accepting electrons, while an element with a highly negative reduction potential, like lithium or potassium, is a genuinely strong reducing agent readily losing electrons. This series also directly, reliably predicts whether one specific reaction between any two given species will actually occur spontaneously. A species will spontaneously reduce, and therefore actually oxidize. Any other species that appears lower than itself in the reduction potential ordered series. This specific principle is exactly why zinc metal spontaneously displaces copper from copper sulfate solution. Zinc sits considerably higher on the reducing strength end of the series than copper does. For calculating standard cell potential of any galvanic cell from tabulated data, always correctly identify which half reaction has the higher standard reduction potential. That one proceeds as written as the cathode, while the other one must be reversed and proceeds as oxidation at the anode. The Nernst equation extends standard electrode potential calculations to genuinely non-standard conditions where concentrations aren't exactly 1 molar, accounting correctly for how cell potential actually changes as a reaction proceeds and concentrations shift away from their initial values. The full equation states that E cell equals E naught cell minus RT over NF times the natural log of the reaction quotient Q, and at the standard, commonly assumed temperature of 25 degrees Celsius, substituting in the known numerical values for R and F and converting from natural log to base 10 log conveniently simplifies this to E cell equals naught cell minus 0.059 over N times log base 10 of Q. This specific simplified numerical form is genuinely worth memorizing directly, since it appears constantly, repeatedly throughout JEE Electrochemistry numericals. As a redox reaction proceeds spontaneously forward, reactant concentrations decrease and product concentrations increase, so reaction quotient Q correspondingly increases, which means E cell must correspondingly continuously decrease over time, and the cell reaches equilibrium, delivering genuinely zero further useful electrical work. Precisely when E cell equals 0 at that specific equilibrium point, the Nernst equation directly gives you a valuable, elegant additional relationship, log base 10 of the equilibrium constant K equals N E naught cell over 0.059, providing a direct, powerful frequently tested bridge connecting electrochemistry data straight to genuine chemical equilibrium calculations. Conductivity kappa measures a solution's genuine ability to conduct electric current per unit length and cross-sectional area, and it depends directly on the actual concentration of ions present in that solution. Molar conductivity, lambda m, normalizes this conductivity specifically by concentration, defined as kappa times 1000, divided by molar concentration, and it allows genuinely meaningful comparison between electrolytes of differing concentrations. For strong electrolytes which are essentially fully completely dissociated into ions even at fairly high concentration, molar conductivity increases only gradually as concentration decreases. Following the Debye-Huckel-Onsager equation, and extrapolating this specific well-behaved linear relationship, all the way to infinite dilution, essentially zero concentration, gives limiting molar conductivity, lambda m naught, directly and reliably from a straight line graph. For weak electrolytes, by contrast, which are only very partially dissociated, molar conductivity increases dramatically, sharply, as concentration decreases, since progressively more dilution genuinely drives further, additional dissociation, and this steep, nonlinear relationship specifically means limiting molar conductivity for weak electrolytes genuinely cannot be found simply by direct graphical extrapolation. It must instead be calculated using Kohlrausch's law of independent migration of ions, which states that limiting molar conductivity of any given electrolyte equals the simple sum of the limiting individual ionic conductivities of its own separate constituent cation and anion. This specific law is exactly what lets you calculate a weak electrolyte's limiting molar conductivity indirectly, by cleverly combining data from several different, strong electrolytes that happen to share common constituent ions. Electrolysis uses externally supplied electrical energy to drive an otherwise genuinely non-spontaneous redox reaction forward, in direct contrast to a galvanic cell, and Faraday's two laws quantify exactly how much chemical change results from a given, known quantity of past electric charge. Faraday's first law states that the mass of substance actually deposited or dissolved at an electrode is directly proportional to the total quantity of electric charge passed through the cell mathematically. Mass equals Z times Q, where Z is the electrochemical equivalent, and Q equals current, multiplied by time. Faraday's second law states that when the identical quantity of electric charge is passed through several different electrolytic cells connected in series, the masses of different substances deposited are direct, proportional to their own individual chemical equivalent weights. This specific law is exactly why comparing deposition at two different electrodes in a series circuit is such a classic fully tested numerical setup. 1 Faraday, defined as exactly 96,500 coulombs, corresponds precisely to the charge carried by exactly 1 mole of electrons, and depositing 1 mole of any singly charge, plus 1 metal ion specifically requires exactly 1 Faraday of charge, while depositing 1 mole of a doubly charged, plus 2 metal ion requires exactly 2 Faradays. Since twice as many electrons must be supplied per mole, or that specific metal ion to achieve full, complete reduction. Primary cells are genuinely single-use, non-rechargeable batteries where the underlying electrochemical reaction is simply not practically reversible. The dry cell, using a zinc container as anode and a carbon rod surrounded by manganese dioxide paste as cathode, and the mercury cell, offering a notably steady constant voltage output throughout its entire discharge lifetime, are classic functionally tested examples. Secondary cells, by contrast, are genuinely rechargeable, since passing external current back through them in reverse can actually restore the original reactance, driving the discharge reaction backward. The lead storage battery used universally in automobiles uses lead as anode and lead dioxide as cathode, both immersed together in sulfuric acid electrolyte, and it can reliably undergo many hundreds of full charge-discharge cycles. The lithium-ion battery, now genuinely dominant in virtually all modern portable electronics and electric vehicles, coax through lithium ions, physically shuttling back and forth between a graphite anode and a metal oxide cathode during charging and discharging, offering a notably high energy-to-weight ratio compared to older battery chemistries. Fuel cells, like the hydrogen-oxygen fuel cell, differ importantly and fundamentally from both primary and secondary batteries, since reactants, hydrogen and oxygen gas specifically, are continuously externally supplied from outside the cell rather than being preloaded and stored internally, allowing genuinely continuous electrical power generation for as long as fuel keeps being actively supplied, with water as the only waste byproduct, making fuel cells a notably clean, environmentally attractive power source. Corrosion, most familiarly the rusting of iron, is fundamentally an unwanted, spontaneous electrochemical process, and understanding it specifically as a genuine galvanic cell forming directly on a metal's own surface makes both its mechanism and its prevention methods considerably easier to understand clearly. In iron's specific case, one region of the metal surface acts as a localized anode, where iron atoms actually oxidize, losing electrons to form iron 2+ ions, while a separate, nearby region acts as a localized cathode, where dissolved atmospheric oxygen is simultaneously reduced, consuming electrons, in the presence of water acting as the essential electrolyte medium connecting these two regions. The iron 2+ ions subsequently further oxidize and combine with water to eventually form hydrated iron oxide, ordinary rust. Corrosion prevention strategies directly exploit this same underlying electrochemical understanding. Barrier protection, like painting or applying a coating, simply physically excludes moisture and oxygen from ever reaching the metal surface in the first place, while sacrificial protection, galvanization, coating iron with a more reactive metal like zinc, works different and more cleverly. Zinc, being higher in the electrochemical reducing strength series than iron, preferentially deliberately corrodes first itself, actively protecting the underlying iron for as long as any sacrificial zinc coating genuinely remains present and intact. This exact same core sacrificial principle is also used directly to protect large buried pipelines and ship hulls, by deliberately electrically connecting them to blocks of a more reactive metal specifically designed to corrode preferentially in their place. For any electrochemistry numerical, follow a consistent, dependable approach. First, correctly identify the anode and cathode by comparing standard reduction potentials. The higher one is always the cathode, and calculate standard cell potential directly as cathode potential minus anode potential, never simply add them together carelessly. Second, if the problem gives non-standard concentrations, immediately reach for the simplified Nernst equation. E cell equals E naught cell minus 0.059 over n log Q, and be very careful to correctly identify n, the specific number of electrons actually transferred in the fully balanced overall cell reaction. An incorrect n value is easily the single most common source of numerical errors throughout this entire chapter. Third, for any electrolysis problems, always start explicitly from charge. Q equals current times time, then convert that charge into moles of electrons by dividing by 96,500, and only then convert moles of electrons into moles, and finally mass, or the actual product, using the correct, specific electron stoichiometry for that reaction. Fourth, for conductance problems, carefully distinguish clearly between conductivity, kappa, and molar conductivity, lambda m, remembering that lambda m specifically requires you to properly divide by concentration first, and always genuinely double-check whether a given problem describes a strong electrolyte, allowing direct graphical extrapolation, or a weak electrolyte requiring Kohlrausch's law instead. A concentration cell is a genuinely special type of galvanic cell where both electrodes are made of the identical material, and the entire cell potential arises purely, exclusively from a difference in ion concentration between the two half cells rather than from any difference in electrode material itself. Electrons flow spontaneously to equalize this concentration difference, with the half cell containing the lower ion concentration always acting as the anode, actively dissolving to increase its own local ion concentration, while the half cell with higher concentration acts as the cathode, depositing metal to decrease its own local ion concentration. Applying the Nernst equation to a concentration cell is genuinely elegant, since both standard reduction potentials are, by definition, identical for identical electrode materials. Enoch et cell itself equals exactly 0, and the entire measured cell potential comes entirely from the logarithmic concentration ratio term alone. The glass electrode pH meter is a particularly important real-world practical application of exactly this same underlying concentration cell principle. It measures a solution's hydrogen ion concentration by measuring the specific potential difference that develops directly across the thin, specialized glass membrane, which is itself selectively specifically sensitive to hydrogen ion concentration on either side, and this measured potential is then precisely related to pH through the Nernst equation, which is exactly why every commercial pH meter genuinely requires periodic calibration, using standard buffer solutions or precisely known pH, to correctly account for any slow, gradual drift in that glass electrode's own actual response characteristics over time and repeated use. Let's recap this entire chapter. Galvanic cells convert spontaneous redox reactions into electricity, with oxidation at the anode and reduction at the cathode, and E cell equals cathode potential minus anode potential, linked to spontaneity through delta G equals minus NF E cell. The Nernst equation, E cell equals E naught minus 0.059 over N log Q, extends this to non-standard conditions, and links directly to equilibrium constants. Molar conductivity, normalized by concentration, behaves differently for strong and weak electrolytes, with Kohlrausch's law needed for weak electrolytes. Faraday's laws quantify electrolysis, with 1 Faraday equal to 96,500 coulombs per mole of electrons, and batteries, plus corrosion, are both real-world applications of these same underlying electrochemical principles. That's the complete electrochemistry chapter for JEE. Keep the Nernst equation and Faraday's laws sharp. Together they cover the overwhelming majority of numericals in this chapter. If this video helped, please like it and subscribe to Padhai Karlo for more JEE preparation content just like this. See you in the next one.